Welcome to this calming and immersive exploration of the mysteries that shape our universe. Over the next 2 hours, we'll delve deep into the fascinating world of physics, mind-boggling facts, and theories that will stretch the limits of your imagination. From the tiniest particles to the vast expanses of space, we'll uncover the hidden truths that govern reality. This journey is designed to relax and enlighten, guiding you through complex ideas in a soothing and gentle way, allowing your mind to wander freely, absorbing each concept at its own pace. Whether you're unwinding after a long day, looking for a peaceful escape, or simply curious about the world around you, this video will take you on a thoughtful journey of discovery. In this first part, Foundations of Reality, we'll begin our exploration with the very building blocks of the universe. From the nature of atoms to the strange and fascinating rules of quantum mechanics, we'll dive into the tiniest details that form everything around us. Let's start by unraveling these foundational ideas as we set the stage for the mysteries ahead. Part 1. Foundations of Reality. Section 1. The nature of atoms. What makes up everything? Atoms are the fundamental building blocks of the universe. Everything around us, from the air we breathe to the stars in the sky, is made up of atoms. These tiny structures, too small to be seen with the naked eye, form the essence of all matter. But what exactly is an atom? An atom consists of a nucleus surrounded by electrons. The nucleus at the center of the atom is made up of protons and neutrons, which are held together by an incredibly strong force. Electrons orbit the nucleus in regions called electron clouds. These tiny particles move at astonishing speeds, making it nearly impossible to pinpoint their exact location at any given moment. The idea that the solid objects around us are actually made up of rapidly moving particles is mind-boggling. Atoms are incredibly diverse, yet they all share the same fundamental structure. Each element in the periodic table corresponds to a different type of atom, distinguished by the number of protons in its nucleus. Hydrogen, the simplest and most abundant element in the universe, has just one proton, while heavier elements like gold and uranium contain many more. The number of neutrons in an atom can vary, giving rise to different isotopes of the same element. These variations can influence an atom's stability and reactivity, playing a crucial role in natural processes like radioactive decay and nuclear fusion. Despite their small size, atoms are powerful. They form chemical bonds to create molecules, which in turn make up everything we see and touch. When atoms combine, they follow specific rules dictated by the electrons in their outermost shells. Some atoms readily share or exchange electrons, forming stable compounds like water or carbon dioxide. Others, like noble gases, resist bonding due to their already complete electron configurations. Understanding these interactions helps scientists predict how substances will behave in different environments, from biological systems to industrial processes. Atoms are not just passive building blocks. They are dynamic and constantly interacting. Chemical reactions occur when atoms rearrange their bonds, releasing or absorbing energy. This is the foundation of everything from the metabolism of food in our bodies to the combustion of fuel in engines. Even the process of breathing involves atoms exchanging places. Oxygen atoms from the air bond with hemoglobin in our blood, sustaining life at the molecular level. Beyond chemistry, atoms hold the key to unlocking some of nature's most profound mysteries. Nuclear energy, for instance, is derived from the splitting or merging of atomic nuclei, releasing immense amounts of energy. Stars, including our sun, generate heat and light by fusing hydrogen atoms into helium, a process that has fueled the cosmos for billions of years. Meanwhile, the study of subatomic particles within atoms has led to groundbreaking discoveries in physics, helping scientists probe the very nature of reality itself. From the tiniest organisms to the vastest galaxies, everything is composed of atoms. Understanding these fundamental units of matter not only deepens our appreciation of the universe, but also empowers us to harness their properties for advancements in science, technology, and everyday life. Atoms may be small, but their impact is boundless, shaping everything we know and experience. Section 2. How small is an atom? Atoms are unimaginably small. To grasp their size, we need to take a journey into a world far beyond what the human eye can see. The objects around us may seem solid and continuous, but at their core, they are made of countless atoms, each so tiny that even the most powerful microscopes struggle to capture their details. To put this into perspective, a single human hair is about 100,000 nanometers wide. An atom, in comparison, is typically less than a nanometer across. That means you could fit hundreds of thousands of atoms side by side across the width of a single strand of hair. If an atom were the size of a marble, a human hair would stretch over a kilometer wide. This scale is so extreme that it challenges our very perception of reality. Even the cells in our bodies, which themselves are microscopic, are enormous when compared to atoms. A typical red blood cell is about 8,000 nanometers in diameter, meaning that thousands of atoms could fit inside it. If we were to shrink ourselves down to the scale of atoms, the world would appear vastly different. The space between atomic particles would seem enormous, and what we perceive as solid matter would be mostly empty space. The reason for this empty space lies in the structure of the atom. The nucleus, which contains nearly all of an atom's mass, is incredibly dense, but occupies only a tiny fraction of the atom's total volume. If an atom were scaled up to the size of a football stadium, the nucleus would be no larger than a marble sitting at the center, while the electrons would be whizzing around in the vast emptiness surrounding it. This strange reality means that even the hardest substances, like diamonds or metals, are mostly empty space at the atomic level. The reason they feel solid is due to the way atoms interact. The electrons in one atom repel the electrons in another, preventing them from passing through each other. This force creates the sensation of solidity, even though, on an atomic level, there is far more emptiness than substance. To truly understand how small an atom is, consider a drop of water. In that tiny droplet, there are more atoms than there are grains of sand on all the beaches of Earth combined. Every sip of water, every breath of air, and every surface we touch is composed of a nearly uncountable number of these tiny, invisible units. Despite their minuscule size, atoms make up everything we see, touch, and experience. The vast emptiness within them is a reminder that the universe operates on scales far beyond human intuition. The deeper we look into the atomic world, the more we realize that what seems ordinary and solid is, in reality, an intricate dance of the smallest building blocks of existence. Section 3. Quantum Mechanics. The Weird Rules of the Tiny World. The world of quantum mechanics is unlike anything we experience in daily life. At the smallest scales, where atoms and subatomic particles exist, the universe follows a set of rules that seem completely bizarre compared to the predictable laws of classical physics. Things do not behave as we expect. Instead, particles can exist in multiple places at once, move through barriers without crossing them, and even influence each other instantly over vast distances. This strange reality governs the fundamental workings of the universe. One of the most mind-bending aspects of quantum mechanics is the concept of superposition. Unlike objects in our everyday world, which exist in definite states, quantum particles can exist in multiple states at the same time. A single electron, for example, does not have a fixed position until it is observed. It exists in a cloud of probabilities, meaning it could be in many places at once. It is only when a measurement is made that the electron chooses a definite location. This idea was famously illustrated by Schrödinger's cat, a thought experiment designed to highlight how strange quantum mechanics truly is. Another strange phenomenon is quantum entanglement. When two particles become entangled, their properties are linked, no matter how far apart they are. If one particle is measured and its state is determined, the other particle instantly takes on a corresponding state, even if it is on the other side of the universe. This appears to violate the principles of relativity, which state that nothing can travel faster than the speed of light. Yet experiments confirm that entanglement is real, though scientists are still trying to understand exactly how it works. The unpredictability of quantum mechanics is further highlighted by the uncertainty principle. This principle states that we can never simultaneously know both the exact position and the exact speed of a particle. The more precisely we measure one property, the less we can know about the other. This is not due to a flaw in our measurement tools, but rather a fundamental aspect of nature itself. The universe, at its core, is built on probabilities rather than certainties. Quantum mechanics also challenges our understanding of cause and effect. In the classical world, we expect events to happen in a logical sequence, where one action leads to another. However, at the quantum level, particles can influence each other in ways that seem to defy time itself. Experiments suggest that the act of observing a particle can change its past behavior, raising deep questions about the nature of reality and whether time flows in the way we assume. Despite its strange and counterintuitive nature, quantum mechanics is not just a collection of weird ideas. It is one of the most successful scientific theories ever developed. It explains the behavior of atoms, allows us to understand chemical reactions, and has led to groundbreaking technologies such as semiconductors, lasers, and quantum computers. The more we explore the quantum world, the clearer it becomes that reality is far more mysterious than we ever imagined. Section 4. Schrödinger's cat paradox. Schrödinger's cat is one of the most famous thought experiments in physics, designed to illustrate the mind-bending nature of quantum mechanics. It was proposed by the Austrian physicist Erwin Schrödinger in 1935 to highlight the strange implications of quantum theory, particularly the concept of superposition. At the heart of this paradox is a simple yet profound question. How can something exist in multiple states at once until it is observed? To understand the thought experiment, imagine a cat placed inside a sealed box along with a small amount of radioactive material, a Geiger counter, a vial of poison, and a hammer. The radioactive material has a 50% chance of decaying within a given time. If it decays, the Geiger counter detects it, triggering the hammer to break the vial and release the poison, killing the cat. If the radioactive material does not decay, the cat remains alive. Since the decay of the radioactive material is governed by quantum mechanics, it exists in a superposition of both decayed and undecayed states until it is observed. According to the strange logic of quantum mechanics, this means that until someone opens the box and observes the cat, it is simultaneously both alive and dead. This idea challenges our everyday understanding of reality. In the macroscopic world that we see and experience, things exist in definite states. A car is either parked or moving. A light is either on or off. But at the quantum level, particles do not behave this way. They exist in a cloud of probabilities, occupying multiple states until they are measured. Schrödinger's cat was meant to show how absurd this concept appears when applied to larger objects, like a living being. The paradox arises from the way quantum mechanics describes reality. In the microscopic world, particles like electrons do not exist in one specific place until they are observed. Instead, they are described by a wave function, a mathematical expression that represents all possible states the system can be in. When a measurement is made, the wave function collapses into one definite state. Before this collapse, all possible outcomes coexist. Schrödinger's thought experiment was not meant to suggest that a real cat could actually be both alive and dead. Instead, he wanted to expose a problem in the interpretation of quantum mechanics, particularly the Copenhagen interpretation, which suggests that particles exist in all possible states until observed. Some physicists believe that the paradox points to deeper questions about the nature of measurement, observation, and consciousness. Others suggest alternative interpretations, such as the many worlds theory, which proposes that each possible outcome exists in a separate parallel universe. Despite the paradox, quantum mechanics remains one of the most successful scientific theories ever developed. Schrödinger's cat continues to be used to explain the strangeness of quantum physics, sparking debates about the true nature of reality. Whether reality truly depends on observation, or whether there is a deeper explanation beyond our current understanding, the paradox challenges us to rethink our assumptions about the universe at its most fundamental level. Section 5. The Uncertainty Principle. The uncertainty principle is one of the most profound ideas in quantum mechanics, revealing a fundamental limit to what we can know about the universe at its smallest scales. Introduced by the German physicist Werner Heisenberg in 1927, it challenges the classical idea that we can measure everything with perfect precision. In the microscopic world of atoms and subatomic particles, reality does not behave in the predictable way we are used to. Instead, there is an unavoidable fuzziness in our ability to measure certain properties at the same time. At the core of the uncertainty principle is the relationship between a particle's position and its momentum. In classical physics, if we know where an object is and how fast it is moving, we can predict exactly where it will be in the future. But quantum mechanics does not allow this level of precision. The more accurately we try to measure a particle's position, the less accurately we can know its momentum, and vice versa. This is not a flaw in our measuring tools or a limitation of technology. It is an intrinsic property of nature. To understand why this happens, it helps to think about how we measure things. When we observe a particle, we typically use light or some other form of radiation to detect it. However, light itself is made of photons, which carry energy. When a photon interacts with a tiny particle like an electron, it disturbs the particle's motion. If we use light with a short wavelength to pinpoint the electron's exact position, the high-energy photon will significantly alter the electron's speed. If we use light with a longer wavelength that does not disturb the electron as much, we lose precision in determining its exact location. This unavoidable disturbance is what leads to the uncertainty principle. The implications of this principle are enormous. It tells us that, at a fundamental level, reality is not as deterministic as classical physics once suggested. Instead of particles following well-defined paths, they exist as probability clouds, where their exact location and motion can only be described in terms of likelihoods. This means that nature operates on probabilities rather than certainties. One of the most surprising consequences of the uncertainty principle is that it allows for strange quantum behaviors, such as particles appearing to tunnel through barriers that, according to classical physics, should be impossible to cross. It also explains why electrons do not simply crash into the nucleus of an atom. They are confined to specific energy levels, creating the structure of matter as we know it. That concludes the first part of our journey, where we've explored the foundational aspects of reality. From the nature of atoms to the peculiarities of quantum mechanics, we've taken a step into the microscopic world that shapes everything around us. As we prepare to move into the next part of our exploration, feel free to let these ideas settle in your mind. Let the calm flow of the universe continue to guide you, and remember, you can pause and reflect on these thoughts whenever you need. Now let's continue our journey, exploring even deeper mysteries in the next part. Part 2: Space, Time, and Relativity. Now that we've explored the foundations of reality, let's take a step further into the nature of space, time, and relativity. Time is something we experience every moment, yet its true nature remains one of the greatest mysteries in physics. How does time work? Can it slow down or even stop? In this part, we'll uncover the strange effects of relativity, time dilation, and even the possibility of time travel. Section 1. What is time? Can it be stopped? Time is one of the most fundamental aspects of our existence, yet defining it is surprisingly difficult. We experience time as a constant flow, moving from the past through the present and into the future. But is time something real, like a physical substance, or is it just a way we perceive change? Scientists and philosophers have debated this question for centuries. At its core, time is deeply connected to motion and change. Without change, whether it's the ticking of a clock, the movement of planets, or the beating of a heart, time would have no meaning. In physics, time is often considered the fourth dimension, working alongside the three spatial dimensions of length, width, and height. Albert Einstein's theory of relativity revealed that time is not absolute but rather flexible, stretching and compressing depending on speed and gravity. This leads to an intriguing question: can time be stopped? Theoretically, yes, under specific conditions predicted by relativity. According to Einstein, time slows down the closer you get to the speed of light. If you could travel at exactly the speed of light, time would stop entirely from your perspective. This means that a photon, a particle of light, does not experience time at all. Another way to stop time is by reaching a region of extreme gravity, such as near a black hole. The immense gravitational pull warps space-time so much that time slows dramatically. At the event horizon, the boundary of a black hole, time appears to freeze from an outside observer's perspective. This phenomenon suggests that under extreme conditions, time, as we know it, can be altered or even brought to a halt. However, for us in everyday life, time continues to move forward, unaffected by our ordinary experiences. While we may never truly stop time, understanding its nature helps us grasp the strange and fascinating ways in which the universe operates. As we move forward, we'll explore how time behaves under Einstein's theory of relativity, the concept of time dilation, and whether traveling through time is more than just science fiction. Section 2. Einstein's theory of relativity explained simply. Einstein's theory of relativity is one of the most groundbreaking ideas in modern physics. It reshaped how we understand space, time, and motion, revealing that the universe behaves in ways that defy common sense. At its core, relativity tells us that time and space are not fixed but flexible, changing based on speed and gravity. While the math behind it can be complex, the basic ideas are surprisingly intuitive when broken down. There are actually two parts to Einstein's theory: special relativity and general relativity. Special relativity, developed in 1905, deals with how time and space behave when objects move at high speeds, particularly close to the speed of light. General relativity, introduced in 1915, expands this idea to include gravity, showing that massive objects can bend space and time. Let's start with special relativity. Before Einstein, most people believed in absolute time and space. The idea was simple. Time ticks at the same rate everywhere, and space is a fixed stage where everything happens. But Einstein realized that this isn't true. Instead, time and space are relative, meaning they change depending on how fast you're moving. One of the most famous consequences of special relativity is time dilation. If you're moving extremely fast, close to the speed of light, time actually slows down for you compared to someone standing still. Imagine two twins. One stays on Earth while the other travels on a spaceship at near light speed. When the traveling twin returns, they will have aged much less than the twin who stayed on Earth. This is known as the twin paradox. And while it sounds like science fiction, it has been confirmed through precise experiments with atomic clocks on fast-moving planes and satellites. Another key idea of special relativity is that nothing can travel faster than light. As an object moves faster, it gains energy, and that energy increases its mass. The closer it gets to the speed of light, the more energy it takes to keep accelerating, making it impossible to reach or exceed light speed. This is why we don't see spaceships zipping across the galaxy at warp speed. Physics simply doesn't allow it. Now, let's move to general relativity, which deals with gravity. Before Einstein, Isaac Newton described gravity as a force pulling objects together, like the Earth pulling on the Moon. But Einstein saw it differently. He proposed that massive objects like planets and stars bend the very fabric of space and time around them. Imagine placing a heavy ball on a stretched-out rubber sheet. It creates a dip that smaller objects roll into. This is how gravity works, according to Einstein. This bending of space and time explains why planets orbit the Sun. Instead of being pulled by an invisible force, they follow curved paths in the warped fabric of space-time. The greater the mass of an object, the more it bends space-time. This effect is most extreme around black holes, where gravity is so strong that even light cannot escape. One of the most stunning confirmations of general relativity came in 1919 during a solar eclipse. Scientists observed that the light from distant stars bent as it passed near the Sun, exactly as Einstein had predicted. This was the first direct proof that gravity could warp space, and it cemented Einstein's status as one of history's greatest scientists. General relativity also explains an important effect called gravitational time dilation. Just as time slows down when you move faster, it also slows down in stronger gravitational fields. For example, if you were near a black hole, time would pass much slower for you compared to someone far away. Even on Earth, this effect is real. Clocks at sea level tick slightly slower than clocks on a mountaintop because gravity is weaker at higher altitudes. Einstein's theory of relativity has changed the way we see the universe. It has led to incredible discoveries, from black holes to the expansion of the cosmos. And while the concepts may seem strange, they are real, shaping everything from GPS technology to our understanding of time itself. Section 3. Time dilation. the faster you move, the slower time goes. Time dilation is one of the strangest and most fascinating effects of Einstein's theory of relativity. It reveals something that seems impossible. Time does not tick at the same rate for everyone. Instead, the faster you move, the slower time flows relative to someone who is standing still. This means that if you were to travel at incredibly high speeds, close to the speed of light, time for you would pass much more slowly than for someone on Earth. This effect comes from Einstein's special relativity, which states that space and time are connected, forming what's called spacetime. When you move through space at high speeds, time adjusts in a way that keeps the laws of physics consistent for all observers. The result is time dilation, where a moving clock runs slower than a stationary one. Imagine two identical clocks. One stays on Earth, while the other is placed on a spaceship traveling near the speed of light. If you compared them after the trip, the clock on the spaceship would show far less time had passed than the one on Earth. This isn't just a thought experiment. Scientists have tested this using extremely precise atomic clocks on fast-moving planes and satellites. Each time, they found that the moving clocks ticked slightly slower, confirming that time dilation is real. Perhaps the most famous example of time dilation is the twin paradox. Suppose one twin remains on Earth while the other takes a journey on a spaceship moving at nearly the speed of light. When the traveling twin returns, they will have aged much less than the twin who stayed behind. While it might sound like science fiction, this effect becomes significant at high speeds and is a real consequence of relativity. The twin paradox theory will be explored further in the next section. Time dilation also happens in the presence of strong gravity. As explained by Einstein's general relativity, the stronger the gravitational pull, the slower time moves. This means that time runs slightly faster on a mountaintop than it does at sea level because gravity is weaker at higher altitudes. This phenomenon has practical applications. GPS satellites, for example, experience both gravitational and velocity-based time dilation. Their onboard clocks tick slightly differently than clocks on Earth, and without constant corrections, GPS positioning would become inaccurate within hours. Time dilation challenges our everyday understanding of time, showing that it is not an absolute fixed thing, but a flexible and relative experience. It raises deep questions about how we experience reality, and even whether time travel could one day be possible. Section 4. The Twin Paradox. The twin paradox is one of the most famous and mind-bending thought experiments in Einstein's theory of relativity. It presents a situation that seems like a contradiction, but is actually a real consequence of how time works at high speeds. The paradox goes like this. Imagine two identical twins. One stays on Earth while the other takes a journey into space on a rocket traveling at nearly the speed of light. When the traveling twin returns, they will be younger than the twin who stayed behind. At first, this seems impossible. After all, from the perspective of the twin on the spaceship, isn't Earth moving away at high speed instead? Shouldn't the effects of time dilation apply equally to both twins? This is where the paradox comes in. It seems like each twin should age slower relative to the other, but in reality, only one of them experiences true time dilation. To understand why, we need to look at special relativity and what happens when motion changes. While the twin on Earth remains in one frame of reference the whole time, the traveling twin experiences acceleration and deceleration when the spaceship turns around to come back. These changes in motion break the symmetry of the situation. Unlike the Earth-bound twin, the traveling twin is not in a single steady frame of reference the entire time. Because of this, the equations of relativity predict that the traveling twin will age significantly less than the one who stayed on Earth. If the journey lasted, say, 50 years on Earth, the traveling twin might have only aged a few years, depending on how close to the speed of light they traveled. When they return, they find that their sibling is now much older than them. This effect isn't just a strange theory. It has been tested in real life. Scientists have sent atomic clocks on airplanes and satellites, and each time they confirmed that the moving clocks ticked more slowly than those on Earth, just as relativity predicts. The twin paradox challenges our intuitive understanding of time and motion, but it is not really a paradox at all. It's a real and measurable phenomenon that reveals the strange and fascinating nature of time itself. And as we explore deeper into relativity, we start to wonder, if time can slow down like this, could we one day use it to travel into the future? Section 5. Could we ever travel through time? Time travel has fascinated humans for centuries, appearing in countless myths, stories, and science fiction tales. But could it actually be possible? According to the laws of physics, the answer is both yes and no, depending on what kind of time travel we're talking about. First, let's look at traveling forward in time. Einstein's theory of relativity already proves that this is not just possible, but actually happens all the time. Thanks to time dilation, the faster you move, the slower time flows for you relative to someone at rest. If a person were to travel at speeds close to the speed of light, they could experience just a few years while decades or even centuries pass for people on Earth. This means that in a sense, traveling into the future is achievable, just not in a way that allows you to come back. We also know that gravity affects time. Gravitational time dilation means that time moves slower in stronger gravitational fields. If you spent time near a massive black hole and then returned to Earth, you would find that more time had passed for people on Earth than for you. Again, this is forward time travel, but not in the way science fiction imagines it. The real challenge is traveling backward in time. This would mean reversing the normal flow of cause and effect, which leads to logical paradoxes, such as the grandfather paradox, where you could travel back and accidentally prevent your own existence. Physics, as we understand it, does not allow time travel into the past, at least not easily. Some theories suggest that it might be possible under extreme conditions. Wormholes, hypothetical shortcuts through space-time, could theoretically connect different points in time as well as space. However, no stable wormholes have ever been discovered, and maintaining one would likely require exotic matter with negative energy, something we don't yet know how to create. Another idea comes from closed time-like curves, solutions to Einstein's equations that suggest space-time could, under certain conditions, loop back on itself. But even if such structures existed, they might be too unstable for actual time travel. For now, traveling into the past remains purely theoretical, and even traveling into the future is limited to extreme speeds or gravity. But as our understanding of physics deepens, who knows? Perhaps one day time travel will move from science fiction to reality. Space, time, and relativity challenge everything we think we know about reality. From the strange slowing of time at high speeds to the paradoxes of time travel, we've seen how the universe operates on rules far beyond our everyday experience. Einstein's insights reshaped our understanding of motion, gravity, and the very fabric of existence. Yet there's still so much more to uncover. The deeper we look, the more the cosmos reveals its mysteries. Part 3. The Universe and its Mysteries. The universe is vast, mysterious, and filled with wonders beyond our imagination. From the moment it began to its ever-expanding nature, scientists have spent centuries trying to unravel its secrets. Space is not just an empty void. It is a dynamic, evolving structure shaped by unseen forces and strange phenomena. In this part, we will explore the origins of the cosmos, the forces driving its expansion, and the mysteries lurking in the darkest corners of space. We begin at the very beginning, with the Big Bang, the event that set everything in motion. Section 1. The Big Bang. How did the universe begin? Everything we see today, the stars, galaxies, planets, and even ourselves, can be traced back to a single moment in time, the Big Bang. This event, which occurred around 13.8 billion years ago, wasn't an explosion in space. Instead, it was the expansion of space itself from an unimaginably small, hot, and dense state. Before the Big Bang, there was no space, no time, and no matter, at least not in the way we understand them. Then, in a fraction of a second, the universe began expanding at an incredible rate. This period, known as cosmic inflation, stretched the fabric of space far beyond what we can observe today. As the universe expanded, it cooled, allowing the first particles to form. In the first few minutes, the basic building blocks of matter, protons, neutrons, and electrons, began to take shape. Hydrogen and helium, the simplest and most abundant elements, were created in this early fireball. But for the first few 100,000 years, the universe remained a hot, glowing plasma, so dense that light couldn't travel freely. Then, about 380,000 years after the Big Bang, something extraordinary happened. Atoms formed, and for the first time, light was able to move freely through space. This ancient light, known as the cosmic microwave background, is still detectable today and serves as a snapshot of the universe in its infancy. From this hot and dense beginning, gravity slowly pulled matter together, forming the first stars and galaxies. Over billions of years, the universe evolved into the vast and complex structure we see today. But how do we know all this happened? The evidence lies in the cosmic microwave background, the abundance of light elements, and the way galaxies are moving apart, clear signs that the universe has been expanding ever since. But if the universe is expanding, where is it headed? And what lies at its edge? To answer these questions, we must explore the ever-growing nature of the cosmos. Section 2. The expanding universe. What's at the edge? Since the Big Bang, the universe has been expanding, growing larger with every passing second. But what does this really mean? If the universe is getting bigger, what exactly is it expanding into? And is there an edge, a final boundary where everything simply ends? These are some of the biggest mysteries in cosmology, and while we don't have all the answers, what we do know is nothing short of mind-blowing. Our understanding of the expanding universe began in the 1920s with the work of Edwin Hubble. Using the world's most powerful telescope at the time, he observed that distant galaxies weren't just sitting still, they were moving away from us. Even more astonishing, the farther away a galaxy was, the faster it was receding. This discovery led to the formulation of Hubble's law, which showed that space itself is expanding, stretching the distance between galaxies. But if the universe is expanding, what is it expanding into? The truth is, it's not expanding into anything. Rather, space itself is growing. A useful analogy is to imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart, not because they are moving on their own, but because the space between them is stretching. The universe works in a similar way, except it expands in all directions, not just across a surface. One of the most astonishing discoveries in modern cosmology is that this expansion is accelerating. Instead of slowing down due to gravity, the universe is expanding faster and faster. Scientists believe a mysterious force called dark energy is responsible, but we'll explore that in the next section. Now, what about the edge? If the universe is expanding, where does it end? The truth is, there may be no edge at all. The observable universe, the part we can see, extends about 46 billion light-years in every direction. But this isn't the full extent of the universe, just the part where light has had enough time to reach us since the Big Bang. Beyond this, there could be far more that we will never be able to observe, simply because the light from those regions hasn't had time to reach us yet. It's possible that the universe is infinite, stretching endlessly with no final boundary. Another possibility is that it's curved and finite, like the surface of a sphere, but in higher dimensions. In this case, traveling far enough in one direction might eventually bring you back to where you started, just like moving across a planet's surface. Edwin Hubble's discovery of cosmic expansion was just the beginning. Since then, astronomers have been uncovering even deeper mysteries about what's driving this growth. To understand the full picture, we must explore the invisible forces shaping the cosmos, dark matter and dark energy, the hidden architects of our universe. Section 3. Dark matter and dark energy, the invisible forces shaping space. The universe we see, the stars, planets, and galaxies, only makes up a tiny fraction of what actually exists. Most of the cosmos is made up of two mysterious invisible forces, dark matter and dark energy. Though we cannot see them, their effects on space are undeniable. They shape galaxies, control cosmic expansion, and hold the universe together in ways we are only beginning to understand. The story of dark matter begins with galaxies. When astronomers observed the motion of stars and galaxies, they found something puzzling. According to Newton's laws, stars at the edges of galaxies should be moving slower than those near the center, just like planets in our solar system orbit slower the farther they are from the sun. But that's not what they found. Instead, outer stars were moving just as fast as inner stars. The only explanation? There had to be invisible mass spread throughout the galaxy, adding extra gravity. This unknown substance was named dark matter because it doesn't emit, absorb, or reflect light, making it impossible to see directly. Scientists estimate that about 27% of the universe is made of dark matter, compared to just 5% of normal matter. But what is it? That's still one of the biggest unanswered questions in physics. Some theories suggest it could be made of undiscovered subatomic particles, while others propose exotic possibilities like modifications to gravity itself. Though we can't see dark matter, we can detect its presence through its gravitational effects. In fact, entire clusters of galaxies are held together by dark matter's invisible grip. Without it, galaxies would fly apart, unable to hold their shape. It's like an unseen glue, keeping the universe in order. If dark matter holds the universe together, dark energy is doing the opposite. It's pushing it apart. While scientists expected the expansion of the universe to slow down due to gravity, observations showed that it was actually speeding up. This shocking discovery in the late 1990s led to the realization that some mysterious force, now called dark energy, was accelerating cosmic expansion. Dark energy is even more dominant than dark matter. Scientists estimate it makes up about 68% of the universe, meaning nearly 3/4 of everything is something we can't see or fully understand. But what is dark energy? One possibility is that it's a property of empty space itself, what Einstein once called the cosmological constant. In this view, space isn't just empty, it has energy, and as the universe expands, more space means more energy, fueling even faster expansion. Another theory suggests dark energy might be linked to an unknown force or a new kind of energy field. Some even speculate that it could be an effect of extra dimensions or a deeper reality we have yet to uncover. Dark matter and dark energy are opposing forces, one pulling inward, the other pushing outward. For billions of years, dark matter's gravity dominated, allowing galaxies to form and cluster together. But as the universe expanded, dark energy took over, causing space to stretch faster and faster. What happens next depends on which force wins. If dark energy continues accelerating the universe's expansion, galaxies will drift apart until the cosmos becomes cold and empty, a fate known as the Big Freeze. If dark energy weakens over time, gravity could eventually slow expansion and pull everything back together, the Big Crunch. And if dark energy fluctuates unpredictably, the universe could even be torn apart in a big rip. For now, dark matter and dark energy remain the biggest cosmic mysteries. We know they're out there, shaping everything we see, but their true nature is still unknown. Unraveling these mysteries could lead to a deeper understanding of the universe, and maybe even new physics beyond our wildest imagination. Section 4. What happens inside a black hole? Black holes are among the most mysterious and extreme objects in the universe. They are regions of space where gravity is so strong that nothing, not even light, can escape. But what happens once you cross the event horizon, the invisible boundary marking the point of no return? The journey inside a black hole is unlike anything in the known universe. As you fall closer, gravity increases exponentially, stretching and squeezing your body in a process called spaghettification. This occurs because the gravitational pull on your feet, if falling feet first, would be far stronger than on your head, elongating you like a noodle. Once past the event horizon, the laws of physics, as we know them, begin to break down. Einstein's general relativity predicts that at the center of a black hole lies a singularity, a point of infinite density where space and time cease to function normally. Matter is crushed into an infinitely small point, and the known laws of physics no longer apply. However, quantum mechanics suggests something different. Some theories propose that black holes may not contain a singularity at all, but rather a chaotic, quantum-dominated core where information is somehow preserved. This idea is at the heart of the black hole information paradox, one of the greatest unsolved mysteries in physics. Another possibility is that black holes could be gateways to other regions of space or even different universes. Some physicists speculate that what lies beyond a black hole's event horizon could be a wormhole, a shortcut through space-time. However, this remains purely theoretical. For now, what happens inside a black hole remains one of the biggest cosmic mysteries, a place where our understanding of the universe reaches its limits. Section 5. Could we survive falling into a black hole? The short answer? No. At least not in any way that allows you to come back and tell the tale. But let's explore why. If you were to fall into a stellar mass black hole, the immense gravity would tear you apart long before you reached the center. This process, known as spaghettification, occurs because the gravitational pull on your feet would be vastly stronger than on your head, stretching you into a thin, elongated strand of atoms. In this scenario, survival is impossible. However, if you were falling into a supermassive black hole, millions or even billions of times the mass of our Sun, the experience might be different. Because the event horizon of such a black hole is much farther from the singular, tidal forces would be weaker at first. In theory, you could cross the event horizon without immediate destruction. But beyond this, things get complicated. Once inside, the crushing gravity would inevitably pull you toward the singularity, where all known laws of physics break down. If Einstein's general relativity holds, no survival is possible. But some theories suggest quantum effects might prevent complete destruction, or that black holes could lead to other regions of space via wormholes, though there's no evidence for this yet. In the end, while black holes remain one of the most intriguing mysteries of the cosmos, surviving a fall into one is purely the stuff of science fiction. At least for now. The universe is a vast, enigmatic place, filled with forces and phenomena that challenge our understanding of reality. From the explosive birth of the cosmos in the Big Bang to the eerie emptiness beyond the expanding universe, we have glimpsed the incredible scales at play. We've explored the unseen forces of dark matter and dark energy, ventured into the heart of black holes, and questioned whether survival inside one is even possible. Part 4. The strangest physics theories. Reality, as we experience it, feels solid, predictable, and singular. But what if everything we know is just one version of an infinite number of possibilities? What if the universe is not what it seems at all? Physics has led us to some of the most bizarre and mind-bending ideas ever conceived, concepts that stretch the limits of imagination and challenge our deepest assumptions about existence. In this part, we explore the strangest theories in modern physics. We begin with the many worlds interpretation, a theory suggesting that every decision we make creates a parallel universe. Then we dive into quantum entanglement, where particles communicate instantly across vast distances. We'll also explore the idea that our reality might be a hologram, consider the fate of information in black holes, and finally ask the ultimate question: are we living in a simulation? Let's step beyond the boundaries of conventional thought and explore the most extraordinary possibilities reality has to offer. Section 1. The Many Worlds Interpretation, Infinite Realities. Imagine standing at a crossroads, forced to choose between two paths. You hesitate, then step forward. In our everyday understanding of reality, you take just one path. But according to the Many Worlds Interpretation (MWI) of quantum mechanics, something much stranger happens. Both choices are made, each leading to a separate, parallel universe. The idea originates from quantum physics, specifically the problem of wave function collapse. In the microscopic world, particles exist in a state of superposition, meaning they exist in multiple states at once. When observed, they collapse into a single state, which is the outcome we see. But what if the wave function never collapses at all? In 1957, physicist Hugh Everett III proposed a radical solution. Instead of collapsing, the wave function splits into multiple realities, each containing a different outcome. In one universe, you turn left, in another, you turn right. Every decision, every quantum interaction, spawns countless parallel worlds, branching out like an endless tree of possibilities. This theory, though fascinating, is difficult to prove. If countless versions of ourselves exist in separate timelines, why can't we perceive them? The answer lies in something called decoherence. Once a quantum system interacts with its surroundings, it becomes part of a larger reality where the different branches cannot communicate with each other. Each world is sealed off, unaware of the others. Despite its strangeness, MWI solves some major issues in quantum mechanics. It eliminates the need for an observer to collapse reality and provides a deterministic view of the universe. Everything that can happen does happen somewhere. It also plays a role in quantum computing, where particles exist in multiple states at once to perform complex calculations. But the implications are unsettling. If MWI is correct, then every choice we make spawns infinite versions of ourselves, each living out different fates. Somewhere, there is a version of you who made a different career choice, one who never met certain people, or one who experienced an entirely different life. Does that mean free will is an illusion, since every possible outcome exists? The many worlds interpretation remains one of the most controversial ideas in physics. Some scientists embrace it, while others reject it as untestable speculation. But whether real or not, it forces us to rethink the nature of reality itself. If infinite versions of you exist, what does that mean for your place in the universe? Perhaps the true mystery is not whether these worlds exist, but why we find ourselves in this particular one. Section 2. Quantum Entanglement. Spooky Action at a Distance. Reality, at its most fundamental level, is far stranger than we ever imagined. Deep in the quantum world, particles can be connected in such a way that the actions of one instantly affect the other, no matter how far apart they are. This phenomenon, known as quantum entanglement, was so bizarre that even Albert Einstein famously called it spooky action at a distance. To understand entanglement, we need to dive into the weird rules of quantum mechanics. Particles, such as electrons or photons, do not have definite states until they are measured. Instead, they exist in a superposition of multiple states at once. But when two particles become entangled, their states become linked, no matter how much distance separates them. Let's take an example. Imagine creating two entangled particles and sending them to opposite ends of the universe. If we measure one particle and find it spinning in a certain direction, the other particle will instantly be found spinning in the opposite direction, even if it's light years away. The key word here is instantly. This connection happens faster than the speed of light. This defies our normal understanding of physics. In Einstein's theory of relativity, nothing can travel faster than light, not even information. But entanglement seems to break this rule, suggesting a hidden connection between the particles that operates outside of space and time. Einstein, along with physicists Podolsky and Rosen, proposed the Fermi Paradox in 1935 to argue that quantum mechanics was incomplete. They believed there must be hidden variables, unknown factors that determine the particle's states before measurement. However, in the 1960s, physicist John Bell developed a mathematical test, now called Bell's theorem, that proved hidden variables could not explain entanglement. Experiments conducted by physicists like Alain Aspect in the 1980s confirmed Bell's predictions. Entanglement is real, and it cannot be explained by local hidden variables. The quantum world truly operates under different rules than our classical intuition suggests. So, what does this mean for our understanding of reality? One possibility is that particles are somehow communicating instantly across vast distances, but this would violate the laws of relativity. Another idea is that space itself is not as it seems, that everything is fundamentally connected at a deeper level we don't yet understand. Some even speculate that entanglement could hint at an underlying fabric of reality, a hidden structure beyond space and time. Despite its mystery, quantum entanglement is not just a theoretical curiosity, it has real-world applications. Quantum cryptography uses entanglement to create ultra-secure communication channels. Quantum teleportation, a technique where the quantum state of a particle is transferred to another instantly, has been demonstrated in laboratories. And quantum computing relies on entanglement to perform calculations exponentially faster than traditional computers. But the biggest question remains. Does entanglement mean that information can travel faster than light? The answer for now is no. While measuring one entangled particle instantly affects the other, this effect cannot be used to send usable information. The randomness of quantum measurement prevents it from being a method of faster-than-light communication. Quantum entanglement challenges everything we know about space, time, and causality. It suggests that the universe is far more interconnected than we ever imagined. Perhaps at the deepest level of reality, everything is entangled in ways we are only beginning to understand. Section 3. The Holographic Universe Theory. What if everything we see, touch, and experience is nothing more than a projection, an illusion created by the universe itself? This is the bold idea behind the holographic universe theory, one of the most mind-bending concepts in modern physics. It suggests that our three-dimensional reality may actually be a hologram, encoded on a distant two-dimensional surface. To understand this, let's first consider how a hologram works. A standard hologram, like those seen on credit cards, is a 2D surface that contains all the information needed to create a 3D image. No matter which angle you look from, the image appears three-dimensional, even though it's actually stored in only 2 dimensions. The holographic universe theory proposes that our entire reality works in a similar way. What we perceive as depth, space, and even time could be an illusion, emerging from information stored on a distant cosmic boundary. But where did this idea come from? In the 1990s, physicists Gerard Hooft and Leonard Susskind developed the holographic principle based on studies of black holes. When matter falls into a black hole, the information about that matter doesn't disappear. It gets stored on the event horizon, the black hole's outer surface. This led scientists to propose that all the information in the universe might be stored in a similar way on a cosmic boundary at the edge of space. A major piece of evidence for this idea comes from string theory, particularly the work of Juan Maldacena, who showed that a certain type of universe with gravity can be mathematically equivalent to a lower dimensional universe without gravity. This means that our perception of gravity and space itself could be emerging from a deeper, two-dimensional reality. If true, the holographic universe would radically change our understanding of reality. Space and time wouldn't be fundamental, they would emerge from underlying information. Some even suggest this could help unify quantum mechanics and general relativity, two of the biggest unresolved problems in physics. While we don't yet have proof that the universe is a hologram, experiments studying the quantum structure of space-time are ongoing. If this theory turns out to be correct, it would mean that everything we experience, our lives, our thoughts, the entire cosmos, could be the result of information projected from the very fabric of the universe itself. Section 4. Can information be destroyed? The black hole information paradox. In physics, one fundamental rule is that information can never be destroyed. Every particle, every event, and every interaction in the universe carries information, details about its past, present, and future. But when it comes to black holes, this rule is challenged, leading to one of the biggest mysteries in physics, the black hole information paradox. Black holes are known for their immense gravity, which pulls in everything, even light, beyond a point called the event horizon. According to Einstein's general relativity, anything that crosses this boundary is lost forever. But quantum mechanics, the science of the very small, tells us that information must always be preserved. This is where the paradox arises. If a black hole swallows an object, what happens to the information that described it? Does it vanish forever, violating the laws of physics? Physicist Stephen Hawking proposed that black holes slowly evaporate over time through Hawking radiation, eventually disappearing completely. But if the black hole disappears, so does the information, creating a direct contradiction with quantum mechanics. Recent theories suggest that information might not be lost but instead encoded in subtle ways at the event horizon or released in some form. The true answer remains unknown, making this paradox one of the most exciting unresolved problems in modern physics. Section 5. Are we living in a simulation? It may sound like science fiction, but some scientists and philosophers believe that our reality might not be real at all. Instead, we could be living inside an incredibly advanced simulation, much like a hyper-realistic video game designed by an advanced civilization. This idea is known as the simulation hypothesis, and it challenges the very nature of existence. One of the strongest arguments for this theory comes from philosopher Nick Bostrom, who proposed that if civilizations continue advancing, they may eventually develop the technology to create highly realistic simulated worlds. If this is possible, then the number of simulated realities could far outnumber the one real reality. Statistically, this would mean that the chances of us living in the original reality are extremely low. Another argument comes from physics itself. Some scientists point to the strange nature of quantum mechanics, where particles seem to behave differently when observed, as if they are being rendered in real time. Others suggest that the fundamental laws of the universe resemble computer code, hinting that our reality might be programmed. Of course, there's no direct evidence proving we live in a simulation. It remains a mind-bending theory, but one that forces us to question reality itself. If we are in a simulation, would we ever be able to detect it? And if we did, what would that mean for the meaning of our existence? The universe is full of mysteries, but perhaps the strangest ideas come from the very nature of reality itself. From infinite parallel worlds to particles defying distance, from the possibility that the universe is a hologram, to the paradox of lost information, and even the mind-bending thought that we might be living in a simulation. These theories push the boundaries of what we know. While we may not have all the answers, exploring these questions brings us closer to understanding the deep, hidden truths of the cosmos. But the mysteries don't end here. Let's continue our journey into the unknown. Part 5. Mind-Boggling Physics Facts. The universe is filled with phenomena that defy intuition and push the limits of human understanding. Some of the most astonishing facts in physics reveal extreme conditions, from the coldest possible temperature to the fastest speeds imaginable. This part will take us on a journey through nature's most fascinating limits: absolute zero, the speed of light, the warping of space by gravity, the incredible density of neutron stars. We will also delve into the smallest possible scale of reality, known as the Planck length, where space and time themselves start to behave in mysterious ways. These aren't just numbers or theories, they shape the very fabric of existence itself. Section 1. Absolute zero, the lowest possible temperature. Temperature is a measure of how fast atoms and molecules move. The hotter something is, the faster its particles vibrate and collide. The colder it gets, the slower they move. But is there a limit to how cold something can be? Yes, and it's called absolute zero, the lowest temperature possible, where all atomic motion nearly comes to a halt. Absolute zero is measured at 0 Kelvin, or minus 273.15 degrees Celsius, which is also minus 459.67 degrees Fahrenheit. At this point, particles lose almost all their kinetic energy. They don't stop moving entirely due to quantum mechanics, but they reach the lowest possible energy state allowed by nature. Achieving absolute zero is impossible because of the laws of thermodynamics. No matter how much energy we remove from a system, there will always be a tiny bit left. However, scientists have come incredibly close. In laboratories, researchers have cooled atoms to just a few billionths of a degree above absolute zero, using advanced techniques like laser cooling and magnetic trapping. At these temperatures, matter behaves in bizarre ways. One of the strangest effects observed near absolute zero is the formation of Bose-Einstein condensates. When a group of atoms is cooled to an extremely low temperature, they start behaving as a single quantum entity, moving in perfect harmony. This allows scientists to study quantum effects on a macroscopic scale. Another fascinating phenomenon is superconductivity, where certain materials lose all electrical resistance when cooled near absolute zero. This discovery has led to advancements in technology, including magnetic levitation and ultra-efficient electrical systems. Though we may never reach absolute zero itself, understanding it helps us push the boundaries of physics and explore the fundamental nature of matter. It is a reminder that the universe operates on rules far stranger than we often imagine. Section 2. The speed of light. Why is it the universe's speed limit? Light is the fastest thing in the universe. It moves at an astonishing speed of 299,792,458 meters per second, roughly 186,282 miles per second. If you could travel at this speed, you could circle Earth about 7 times in just 1 second. But why is this the ultimate speed limit? Why can't anything go faster? To understand this, we have to go back to Einstein's theory of relativity. According to his famous equation, E equals mc squared, energy and mass are deeply connected. The faster an object moves, the more energy it needs. But as an object approaches the speed of light, its mass effectively increases, requiring even more energy to keep accelerating. At 99% of the speed of light, the energy required becomes enormous. At 100%, it would become infinite. Since infinite energy is impossible to achieve, no object with mass can ever reach the speed of light. Light itself is an exception, because it has no rest mass. This allows photons, particles of light, to travel at the speed limit without needing infinite energy. But for everything else, from planets to spaceships to humans, this speed is completely out of reach. The speed of light is not just a fast number, it's a fundamental constant of the universe. It governs how space and time behave. If you were somehow able to travel close to this speed, time would slow down dramatically for you due to time dilation. Distances would contract, and the universe would appear drastically different. This is why traveling faster than light is not just a technological challenge. It would require breaking the laws of physics as we know them. But what if there was a way around this limit? Scientists have speculated about concepts like wormholes or warp drives, which could bend space itself to allow faster-than-light travel. However, these ideas remain purely theoretical, and we have no experimental evidence that they are possible. For now, the speed of light remains the cosmic speed limit, defining the boundaries of what we can explore and experience in the universe. It is a fundamental constraint, yet it also holds the key to some of the deepest mysteries in physics. Section 3. How gravity bends light. Gravity, the invisible force that keeps our feet on the ground and planets in orbit, also has a profound effect on light itself. This phenomenon, known as gravitational lensing, is a direct consequence of Einstein's general theory of relativity. It tells us that massive objects like stars, black holes, and entire galaxies warp the very fabric of space-time around them. And when light from distant sources passes through this distorted space, it bends, just as a glass lens bends light to focus an image. To understand why this happens, we need to rethink gravity, not as a simple force, but as a curvature of space and time. Imagine placing a heavy ball on a stretched-out rubber sheet. The ball creates a dent in the sheet, and if you roll a marble close to it, the marble's path curves inward. This is similar to what happens when light travels through space that has been warped by gravity. Even though light moves in a straight line, it follows the curves of space-time itself, appearing to bend around massive objects. One of the most famous confirmations of this effect came in the year 1919 during a solar eclipse. British astronomer Sir Arthur Eddington tested Einstein's predictions by observing the apparent positions of stars near the Sun. The Sun's gravity slightly bent the incoming starlight, shifting their apparent locations in the sky. This was groundbreaking because it provided direct evidence that space itself is curved by mass, just as Einstein had predicted in his equations. The most spectacular and useful examples of gravitational lensing occur on a cosmic scale. When light from a distant galaxy or quasar encounters a massive galaxy or cluster in its path, it bends around the intervening object. Sometimes, this effect magnifies and distorts the background light, stretching it into arcs or even creating multiple images of the same object. Astronomers have spotted stunning cases where entire galaxies appear duplicated or arranged in circular patterns, known as Einstein rings. These cosmic lenses help scientists study galaxies that would otherwise be too faint or far away to observe directly. One of the most extreme examples of light bending occurs near black holes. A black hole's gravity is so strong that it doesn't just bend light, it can trap it completely if it crosses the event horizon, the point of no return. But just outside this boundary, light can take incredibly twisted paths. In some cases, photons can orbit the black hole before escaping, causing strange optical illusions, where the backside of a black hole appears mirrored around its edges. Beyond creating mesmerizing images, gravitational lensing plays a crucial role in modern astronomy. Scientists use it to map the distribution of dark matter, the mysterious, invisible substance that makes up most of the universe's mass. Since dark matter doesn't emit or reflect light, astronomers detect it by observing how its gravity bends light from distant galaxies. The more distortion they see, the more dark matter is present in that region of space. This bending of light also helps us understand the expansion of the universe. By studying how gravitational lenses stretch and magnify distant objects, astronomers can measure cosmic distances with incredible precision. This allows them to test theories about how the universe has evolved over billions of years. Perhaps most mind-boggling of all, gravitational lensing allows us to see into the past. Because light from the farthest galaxies has traveled for billions of years before reaching us, their images appear as they were when the universe was much younger. By studying these lensed objects, scientists are essentially looking back in time, uncovering secrets about the early cosmos. In the grand scheme of the universe, gravity's ability to bend light is more than just a quirk of physics. It's a powerful tool that helps us explore the deepest mysteries of space. It confirms the mind-bending reality that space itself is not a rigid, empty stage, but a dynamic, flexible fabric shaped by the mass and energy it contains. Through the lens of gravity, the universe reveals itself in ways that continue to challenge and expand our understanding. Section 4. Neutron stars, the densest objects in the universe. Neutron stars are among the most extreme objects in the universe. They form when massive stars reach the end of their lives in a violent supernova explosion. What remains is an incredibly dense core, packed so tightly that even atoms collapse, leaving behind a sphere of nearly pure neutrons. These stars may be only about 12 miles across, but they contain more mass than our Sun, making them the densest known objects outside of black holes. To understand how extreme a neutron star is, imagine compressing a mountain into the size of a marble. A single teaspoon of neutron star material would weigh about 1 billion tons, roughly the same as a mountain on Earth. This immense density arises because gravity forces protons and electrons to merge, forming neutrons and eliminating the empty space that usually exists in atoms. The result is a star that is just one step away from becoming a black hole. Neutron stars are not just dense, they are also incredibly hot and fast-spinning. Many neutron stars rotate hundreds or even thousands of times per second. This rapid spin is due to a principle called conservation of angular momentum. When a large star collapses into a tiny neutron star, it spins much faster, just like a figure skater pulling in their arms. Some of the fastest known neutron stars, called millisecond pulsars, rotate over 700 times per second. One of the most fascinating types of neutron stars is the pulsar. Pulsars emit beams of radiation from their magnetic poles, which sweep across space like cosmic lighthouses. When these beams point toward Earth, they create a pulsing effect, leading to their name. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, and at first, scientists thought it might be a signal from an alien civilization. These pulsars are now used as cosmic clocks because of their extreme regularity, helping scientists study space-time and even detect gravitational waves. Neutron stars also have some of the strongest magnetic fields in the universe. A special type called a magnetar has a magnetic field trillions of times stronger than Earth's. If a magnetar were placed halfway to the Moon, its magnetic force could erase credit card data on Earth. These intense magnetic fields can cause bursts of high-energy radiation, which scientists detect as powerful gamma-ray and X-ray flares. Despite their small size, neutron stars play a crucial role in the cosmos. When two neutron stars collide, they create some of the most powerful explosions in the universe, known as kilonovae. These collisions produce heavy elements like gold and platinum, seeding the universe with the materials that make up planets and even life itself. In 2017, astronomers detected gravitational waves from a neutron star merger, confirming that these events are responsible for much of the heavy elements found on Earth. Section 5. The Planck length, the smallest possible scale of reality. The Planck length is an incredibly small unit of measurement that represents the smallest possible scale of space and time in the universe. It's so tiny that it's almost beyond our comprehension. The Planck length is vastly smaller than the size of subatomic particles like protons and neutrons. To put this into perspective, if you were to compare the Planck length to the size of an atom, it would be like comparing the entire observable universe to a single atom. The Planck length is based on fundamental constants in physics, namely the speed of light, Planck's constant, and the gravitational constant. These constants are key to understanding the universe's deepest workings. When these constants are combined, they give us the Planck length, marking the point at which our current understanding of physics breaks down. It's essentially the smallest possible length that has any physical meaning. At scales smaller than the Planck length, space and time no longer behave as we expect. In this realm, quantum gravitational effects are believed to become significant, and the fabric of space-time itself may become quantized. This means that space and time might not be smooth and continuous, as we usually imagine, but instead might be composed of tiny, discrete units, much like grains of sand on a beach. This idea is at the heart of theories attempting to unify quantum mechanics and general relativity, two pillars of modern physics that, until now, have been difficult to reconcile. While the Planck length is far beyond the reach of current experimental technology, its existence is fundamental to our understanding of the universe at the most fundamental level. It's a boundary between the realms of quantum mechanics and classical physics, where the very nature of space and time might be profoundly different from what we experience every day. And with that, we've reached the end of this part. From absolute zero to the smallest scales of reality, we've explored some of the most mind-boggling aspects of the universe. Stay tuned as we continue to unravel even more fascinating mysteries in the next part. Part 6. Parallel Universes and Dimensions. The nature of reality may be far more complex than what we perceive. While we move through 3 dimensions of space and experience time as a 4th, theories in modern physics suggest that our universe might be hiding additional dimensions beyond our senses. These hidden dimensions could shape the fundamental laws of nature and even open the door to parallel universes. In this part, we explore the possibility of extra dimensions, the mind-bending concept of wormholes, the expansion of the cosmos, the unpredictability of chaos, and whether an infinite universe means another version of you exists somewhere. Section 1. Do extra dimensions exist? For most of human history, the world was understood in terms of 3 dimensions: length, width, and height. Time, often considered separate, became recognized as a 4th dimension with Einstein's theory of relativity. But what if there are more? Some of the most advanced theories in physics suggest that reality might be shaped by additional, hidden dimensions that we simply cannot perceive. One of the most well-known frameworks that require extra dimensions is string theory. This theory proposes that the fundamental building blocks of the universe are tiny vibrating strings, rather than point-like particles. For the math behind string theory to work, it demands the existence of more than just 4 dimensions. Some versions require up to 11. These extra dimensions would be compact and hidden at scales so small that they are beyond our ability to detect, curled up within the fabric of space itself. But if these dimensions exist, why can't we see or experience them? Think of a tightrope walker moving along a rope. To them, the rope seems like a simple one-dimensional path, forward or backward. But a tiny ant crawling on the rope would experience another dimension, moving around its circumference. In the same way, these extra dimensions might exist, but only at scales much smaller than what we can observe. The idea of extra dimensions isn't just a mathematical trick. If they exist, they could have profound effects on the universe. Some theories suggest that gravity is weaker than the other fundamental forces because it spreads into these extra dimensions, while forces like electromagnetism remain confined to our familiar 4-dimensional world. If this is true, experiments designed to measure gravity at extremely small distances might one day detect evidence of hidden dimensions. Physicists are searching for clues in high-energy experiments like those at the Large Hadron Collider. Some theories predict that when particles collide at extreme energies, they could momentarily create effects that hint at extra dimensions. So far, no direct evidence has been found, but the search continues. Another intriguing idea is that extra dimensions could be linked to parallel universes. If these dimensions exist on scales larger than we imagine, it's possible that entire other universes exist alongside ours, separated by a tiny distance in a dimension we can't access. This raises the question of whether travel between these dimensions is possible, and if so, how it could be done. While extra dimensions remain hypothetical, they offer an exciting glimpse into a reality far beyond our everyday experience. If they do exist, they could hold the key to unifying all of physics and explaining some of the deepest mysteries of the universe. Section 2. Could wormholes connect different universes? The idea of wormholes is one of the most thrilling concepts in physics, often appearing in science fiction as cosmic shortcuts through space and time. But could these mysterious tunnels actually exist? And if they do, could they serve as gateways between different universes? While no wormhole has ever been observed, the mathematics of general relativity suggests they might be possible. And if so, they could redefine our understanding of the cosmos. A wormhole, also known as an Einstein-Rosen bridge, is a theoretical structure that acts as a shortcut through space-time. Instead of traveling vast distances across the universe, a wormhole could provide an almost instantaneous route between two distant points. Imagine space as a two-dimensional sheet of paper. If you wanted to travel from one side to the other, you would have to move across the surface. But if you fold the paper so that the 2 points touch, you could simply step from one to the other. This is the basic idea behind a wormhole. Einstein's general theory of relativity allows for the existence of these tunnels in spacetime. In fact, black holes themselves are closely related to the idea of wormholes. The extreme warping of space by a black hole suggests that if two such objects were connected, they might form a tunnel linking different regions of the universe. However, there's a major problem. Naturally forming wormholes, if they exist, are likely to be unstable. As soon as anything, even light, tries to pass through, they would collapse almost instantly. For a wormhole to remain open, it would require a form of matter with negative energy, often called exotic matter. Unlike normal matter, which has positive energy and mass, exotic matter would push outward rather than pull inward, preventing the tunnel from collapsing. Some theories suggest that quantum effects might allow for such exotic matter to exist in tiny amounts, but no one has ever observed it. Without this stabilizing force, wormholes would be too fragile to function as cosmic shortcuts. If stable wormholes do exist, they might not only connect distant points in space, but also link different universes entirely. The concept of a multiverse, a vast collection of parallel universes existing beyond our own, is an exciting possibility in modern physics. Some theories suggest that these universes could be connected by wormholes, meaning a traveler who enters one might emerge in a completely different cosmos with its own physical laws. Could humans ever travel through a wormhole? Even if one were discovered, there would be enormous challenges. First, entering a wormhole would likely expose travelers to extreme gravitational forces that could tear them apart. Second, if a wormhole led to another universe, there's no guarantee that it would be possible to return. It's also possible that different universes have entirely different rules of physics, making survival impossible. Scientists are exploring ways to detect wormholes, although no direct evidence has been found. Some physicists speculate that if a wormhole exists, it might distort the light from distant stars in a unique way, creating a distinct observational signature. Others propose that extremely advanced civilizations, if they exist, might have already created artificial wormholes for travel. Whether or not wormholes truly exist, they remain one of the most fascinating possibilities in theoretical physics. If we one day uncover proof that they are real, it could open the door to an entirely new way of exploring the cosmos, connecting not just distant corners of our universe, but perhaps even entirely different realms of existence. Section 3. The theory of cosmic inflation. The universe as we know it is vast, mysterious, and seemingly infinite, but how did it all begin? The Big Bang theory explains that the universe started as an incredibly hot and dense point around 13.8 billion years ago. However, this theory alone cannot explain some of the biggest puzzles about the cosmos. Why does the universe look so uniform in every direction? Why does space seem to be so flat instead of curved? And how did tiny quantum fluctuations in the early universe grow into the galaxies and structures we see today? To answer these questions, physicists introduced the theory of cosmic inflation, a brief but extraordinarily rapid expansion of the universe that happened within the first tiny fraction of a second after the Big Bang. According to this idea, the universe expanded exponentially, growing from a size smaller than an atom to a macroscopic scale in less than a trillionth of a second. This sudden inflation stretched out any irregularities and set the stage for everything that followed, from the formation of galaxies to the distribution of cosmic radiation. One of the biggest mysteries inflation solves is the horizon problem. The universe looks remarkably uniform, whether we observe galaxies billions of light-years away or look at the cosmic microwave background radiation, which is the afterglow of the Big Bang. Everything appears to have nearly the same temperature. The problem is that, under normal expansion, distant regions of space should never have been able to exchange heat or information, meaning they shouldn't have had time to reach the same temperature. Inflation solves this by proposing that before the expansion, these regions were much closer together and could interact. Then, as space rapidly expanded, they were stretched apart, explaining why the universe appears so uniform today. Another major problem inflation helps explain is the flatness problem. According to Einstein's general theory of relativity, space can be curved, either positively like a sphere, negatively like a saddle, or completely flat. Observations show that the universe is incredibly close to being flat, which is surprising because, over billions of years, even the slightest initial curvature should have grown dramatically. Inflation explains this by stretching space so much that any initial curvature became insignificant, just as a small bump on a balloon becomes nearly invisible when the balloon is blown up to an enormous size. Inflation also provides an explanation for the origins of galaxies and cosmic structure. Before inflation, tiny quantum fluctuations, random variations at the smallest scales, existed in the fabric of spacetime. As inflation expanded the universe at an exponential rate, these tiny fluctuations were stretched into much larger structures. Over time, these small variations became the seeds of galaxies, clusters, and the vast cosmic web we see today. Without inflation, it's difficult to explain how such large-scale structures could have formed from the early universe. So, what caused inflation, and what made it stop? The most widely accepted idea is that inflation was driven by a hypothetical energy field known as the inflaton field. This field contained a huge amount of energy that drove space to expand at an accelerating rate. Eventually, the energy of this field was transferred into ordinary matter and radiation, marking the end of inflation and the beginning of the more gradual expansion we observe today. However, physicists still do not know exactly what the inflaton field is or what its properties might be. Inflation also raises fascinating questions about the nature of the cosmos. Some versions of the theory suggest that inflation never truly stops, but instead continues eternally in some regions of space. This idea, known as eternal inflation, suggests that while our observable universe stopped inflating and became what we see today, other parts of the cosmos are still expanding at an incredible rate. If this is true, it could mean that our universe is just one small bubble in a much larger multiverse, where other bubble universes could have formed with completely different physical laws and properties. Despite its successes, inflation is still a theoretical concept, and scientists are searching for more evidence to confirm it. One key piece of evidence comes from the cosmic microwave background radiation, the faint glow left over from the early universe. The detailed patterns in this radiation match predictions made by inflationary models, providing strong support for the theory. Scientists are also looking for a specific signature known as primordial gravitational waves, ripples in spacetime that inflation should have created. If detected, these waves would be direct proof that inflation occurred. The theory of cosmic inflation has transformed our understanding of the early universe, solving many of the mysteries that the Big Bang theory alone could not explain. While there is still much to learn, inflation provides a compelling picture of how the universe evolved from a tiny quantum fluctuation into the vast cosmic landscape we see today. If future observations continue to support this idea, it may bring us one step closer to understanding the deepest secrets of the cosmos. Section 4. The Butterfly Effect and Chaos Theory. The universe often appears to follow predictable patterns, governed by laws of physics that allow us to make accurate predictions. However, in certain systems, even the smallest change in initial conditions can lead to drastically different outcomes over time. This idea is at the heart of chaos theory, a field of mathematics and physics that studies how small variations can produce unpredictable and seemingly random results. One of the most famous concepts within chaos theory is the butterfly effect, which suggests that a tiny event, such as the flap of a butterfly's wings, could potentially lead to significant changes in a system, such as triggering a tornado weeks later. The butterfly effect was first introduced by Edward Lorenz, a meteorologist and mathematician, in the early 1960s. While working on weather prediction models, he discovered that tiny differences in starting conditions led to wildly different weather patterns over time. This meant that long-term weather forecasting was fundamentally limited because even the slightest unknown factor could drastically alter future outcomes. He described this phenomenon with a thought experiment. A butterfly flapping its wings in Brazil could set off a chain of atmospheric events that eventually cause a tornado in Texas. At its core, chaos theory explains that while chaotic systems follow deterministic laws, their outcomes are highly sensitive to initial conditions. This is often referred to as sensitive dependence on initial conditions. In other words, even though the system is governed by precise mathematical rules, tiny uncertainties or changes can make long-term predictions practically impossible. Some common examples of chaotic systems include weather patterns, planetary orbits, stock markets, and even human brain activity. One well-known example of chaos theory in action is the double pendulum, a simple system with two connected swinging arms. While a single pendulum follows a predictable path, adding a second joint makes the system incredibly chaotic. Even the slightest difference in how it is set in motion leads to a completely different trajectory over time, making it impossible to predict its movements after a few swings. Chaos theory has profound implications beyond just physics. It applies to fields like biology, where small genetic mutations can lead to major evolutionary changes, and economics, where minor shifts in market conditions can trigger financial crises. It also plays a role in neuroscience, as the human brain is a complex system with unpredictable behaviors emerging from tiny neural interactions. The butterfly effect and chaos theory remind us that while the universe follows laws of physics, not everything is predictable. In many cases, the smallest details can shape the biggest events, making the world far more interconnected and complex than it seems at first glance. Section 5. If the universe is infinite, is there another you out there? The idea of an infinite universe raises a fascinating possibility. If space goes on forever, could there be another version of you somewhere out there? This concept is rooted in the idea that in an infinite cosmos, everything that can happen must happen an infinite number of times. Our observable universe, the region we can see, is limited by the speed of light and the age of the universe. Beyond this boundary, space may continue indefinitely. If the universe is truly infinite, then there are only a finite number of ways to arrange particles in a given region. Eventually, those arrangements would have to repeat, just like how a shuffled deck of cards will eventually return to the same order if shuffled an infinite number of times. This suggests that, far beyond our visible universe, there could be another Earth, another solar system, and even another person identical to you. This idea is closely linked to the concept of a multiverse, where infinite cosmic regions may contain all possible variations of reality. However, even if these duplicates exist, they are so unimaginably far away that we could never reach them, making this a purely theoretical discussion. While it's impossible to know for certain, the idea that another version of you might exist somewhere in the vast expanse of space is both unsettling and awe-inspiring. With that, we conclude this part, having explored parallel universes, extra dimensions, the mysteries of cosmic infinity, and how even the smallest changes, the butterfly effect, can ripple through space and time in unpredictable ways. Part 7. Mysteries of the Cosmos. The cosmos is full of unsolved mysteries, and our quest to understand it is far from complete. From the possibility of extraterrestrial life to the strange phenomena that lie beyond our reach, the universe continues to surprise and baffle us. In this part, we'll explore some of the most intriguing questions about the cosmos. We'll look at why, despite the vastness of space, we haven't yet found signs of alien civilizations and what that might mean. We'll delve into the wow signal, a potential message from aliens, and the concept of Dyson spheres, structures that could harness a star's energy. Finally, we'll consider whether humanity is truly ready for contact with extraterrestrial civilizations. These are the questions that keep scientists and dreamers alike wondering. Are we alone? And if not, where is everybody? Section 1. The Fermi Paradox. Where is everybody? The universe is vast, and the possibility of extraterrestrial life has captivated human imagination for centuries. Given the sheer size of the cosmos, it seems inevitable that we should find evidence of alien civilizations. However, there's a deep mystery that haunts astronomers and scientists alike. If there are so many potentially habitable planets out there, why haven't we detected any signs of intelligent life? This is the essence of the Fermi Paradox, one of the most perplexing questions in modern science. The Fermi Paradox is named after physicist Enrico Fermi, who famously asked, "Where is everybody?" while discussing the possibility of extraterrestrial civilizations. The paradox is built on two key assumptions. First, the vastness of the universe, which contains billions of stars, each potentially having habitable planets. And second, the idea that intelligent life should, in theory, have had enough time to spread throughout the galaxy. The numbers are staggering. The Milky Way alone is home to around 100 billion stars, and recent studies suggest that a significant percentage of these stars have planets orbiting them, many of which could be in the habitable zone, where conditions might be right for life. If life emerged on Earth, it stands to reason that it could also emerge elsewhere, and possibly even develop into advanced civilizations. Given the age of the galaxy, billions of years older than Earth, it seems unlikely that we're the only ones. So the question arises, if intelligent civilizations exist, why haven't we found them? There are several possible explanations for the Fermi Paradox. One theory is that extraterrestrial civilizations are out there, but they are simply too far away for us to detect. The vast distances between stars make it incredibly difficult for signals or even spacecraft to travel across the galaxy. The nearest star system to us, Alpha Centauri, is over 4 light-years away, and even if we were to receive a signal, it could take decades or even centuries to decode it. It's also possible that alien civilizations exist, but their technology is so different from ours that we can't recognize their signals. Another theory is that intelligent civilizations may be deliberately avoiding us. In this scenario, advanced alien civilizations are aware of Earth and choose not to make contact, perhaps out of caution or a prime directive, similar to the one seen in science fiction, where more advanced civilizations avoid interfering with less developed ones. The zoo hypothesis suggests that Earth is like a zoo or nature reserve, with extraterrestrials observing us from a distance without interfering in our development. A third possibility is that intelligent civilizations are rare or short-lived. Perhaps life does emerge on many planets, but civilizations that reach a high level of technological advancement self-destruct before they can make contact with others. This could happen through nuclear war, environmental collapse, or the unintended consequences of advanced technology. If intelligent life is short-lived, the window of time during which civilizations can communicate with each other might be incredibly narrow. There's also the possibility that we're simply not looking for the right signs. Our current technology might not be advanced enough to detect alien civilizations, or we might be looking in the wrong frequencies. We've only begun to explore the universe in terms of detecting signals, and it's possible that extraterrestrial communications are outside our current range of detection. Finally, there's a more philosophical answer to the Fermi Paradox. Perhaps we are indeed alone in the universe. While this seems unlikely given the vast number of stars and planets, the idea that Earth is the only cradle of intelligent life in the cosmos remains a possibility, albeit a humbling one. Section 2. Are we alone in the universe? The question of whether we are alone in the universe is one of humanity's oldest and most profound. With billions of stars in our galaxy alone, and countless more galaxies stretching across the cosmos, it seems statistically improbable that Earth is the only planet harboring life. Yet, despite the vastness of space, we have found no definitive evidence of extraterrestrial life, leaving the question open-ended. Scientists have long searched for signs of life beyond Earth using several methods, from studying the conditions on exoplanets to sending signals into space, hoping to receive a response. One of the most promising areas of exploration involves the study of exoplanets, planets that orbit stars outside our solar system. Many of these planets are in the habitable zone, where conditions may allow for liquid water, a key ingredient for life as we know it. As our technology advances, we're able to detect planets that might possess the right conditions for life, yet we've yet to find direct evidence of life itself. Astronomers also look for biosignatures or chemical traces in the atmospheres of distant planets, which could indicate biological processes. But so far, while some planets show promise, no conclusive proof of life has been found. This lack of evidence, combined with the vastness of the universe, has led some to question whether intelligent life is out there, or if Earth is truly unique. While we haven't yet discovered extraterrestrial life, it's important to consider the implications of finding it. The discovery of even simple microbial life elsewhere would dramatically shift our understanding of life's origins and our place in the universe. Until that moment comes, we remain in a state of profound curiosity, wondering if we're truly alone, or if life exists somewhere else in the infinite expanse of space. Section 3. The WOW signal. A message from aliens? On August 15, 1977, a strong and unexplained radio signal was detected by astronomer Jerry Amon while working on the Big Ear radio telescope at Ohio State University. The signal lasted for 72 seconds and came from the direction of the constellation Sagittarius. It was so remarkable that Amon circled it on the printout and wrote "WOW" in red ink, giving the event its now famous name, the WOW signal. The signal stood out because it was a narrowband radio transmission, which is unusual because natural cosmic sources, such as stars or quasars, typically emit a broad range of frequencies. The WOW signal was detected at 1,420 MHz, a frequency known as the hydrogen line, which scientists believe could be an ideal channel for interstellar communication. Hydrogen is the most abundant element in the universe, and intelligent civilizations might choose this frequency for transmitting messages, expecting others to recognize its significance. Despite its intriguing characteristics, the signal was never detected again. Repeated efforts to find a similar transmission from the same region of space have failed, leaving scientists puzzled. If it were truly an artificial signal, why was it never repeated? Could it have been an intentional transmission from an extraterrestrial civilization? Or was it simply an unusual but natural cosmic phenomenon? Over the years, many theories have been proposed to explain the WOW signal. Some suggest it was a reflection of an Earth-based signal bouncing off space debris. Others speculate that it could have originated from a passing comet, which may have emitted a radio burst as it traveled through space. However, none of these explanations have been definitively proven, and the mystery remains unsolved. If the WOW signal truly came from an intelligent alien civilization, it would represent one of the most significant discoveries in human history. But without a repeat detection, we can only speculate about its origins. The signal serves as a reminder that the search for extraterrestrial intelligence is filled with both excitement and frustration. While the WOW signal remains unexplained, it continues to inspire scientists and enthusiasts to keep listening to the cosmos, hoping that one day we might receive a definitive message from the stars. Section 4. Dyson spheres. A way to harness a star's energy. A Dyson sphere is a hypothetical megastructure that could be built around a star to capture its energy. First proposed by physicist and mathematician Freeman Dyson in 1960, the idea suggests that an advanced civilization could construct an enormous shell or swarm of structures around a star to harness its immense power. The concept was inspired by the idea that as civilizations grow, their energy demands increase, eventually surpassing what can be generated on a single planet. The most basic version of a Dyson sphere is a solid shell completely enclosing a star. However, this design presents enormous engineering challenges, including immense gravitational forces and material constraints. More realistic models, such as a Dyson swarm, propose a collection of orbiting satellites that collectively capture and transmit energy back to the civilization using them. A Dyson ring, a simpler version, consists of a series of energy-collecting stations in a stable orbit around the star. If an advanced extraterrestrial civilization had built a Dyson sphere, it might be detectable from Earth. A fully enclosed star would not emit visible light, but it would still radiate heat in the form of infrared energy. Astronomers have searched for unusual infrared signatures that could indicate the presence of such a structure, but no conclusive evidence has been found so far. The concept of a Dyson sphere raises profound questions about the future of human civilization. If humanity continues to advance technologically, could we one day build such a structure? The energy from even a fraction of the sun's output would be enough to power our civilization for millions of years. While still in the realm of science fiction, the Dyson sphere remains a fascinating idea that challenges our understanding of what is possible in the pursuit of limitless energy. Section 5. Are we ready for contact with extraterrestrial civilizations? The idea of making contact with an extraterrestrial civilization is both thrilling and unsettling. If we were to receive an undeniable signal from an intelligent alien species, or even encounter them directly, would we be prepared? The answer is not straightforward. While scientists, governments, and even international organizations have considered the possibility, there is no global consensus on how to respond. One of the biggest challenges is uncertainty. We have no idea what form alien life might take, how they would communicate, or what their intentions might be. Some scientists argue that making our presence known to the cosmos, through efforts like sending radio signals into space, could be risky. If an advanced civilization were to discover us, we cannot predict whether they would be friendly, indifferent, or hostile. Socially and psychologically, humanity may not be ready. Throughout history, encounters between civilizations with different levels of technological advancement have often led to conflict. Even if extraterrestrials have peaceful intentions, their mere existence could challenge fundamental human beliefs about our place in the universe. Some people might react with excitement, while others could panic or reject the idea altogether. Despite these concerns, efforts are in place to prepare for such an event. Scientists at the Search for Extraterrestrial Intelligence have discussed possible response protocols, and space agencies like NASA have explored the implications of first contact. However, until the moment arrives, we won't truly know how humanity will react. Whether we are ready or not, the possibility of alien contact remains one of the greatest unknowns of our time. As we explore the mysteries of the cosmos, one question remains unanswered. Are we truly alone? From the puzzling silence of the Fermi Paradox to the intriguing wow signal, the search for extraterrestrial intelligence continues. Whether through advanced megastructures like Dyson spheres or the possibility of direct contact, the idea of alien life challenges our understanding of the universe and our place within it. With this, we conclude this part, but the mysteries of the cosmos remain as vast and uncertain as ever. Part 8. Physics and Human Existence. The connection between physics and human existence is one of the most profound mysteries of all. While physics helps us understand the universe on a grand scale, it also raises deep questions about life, consciousness, and our ultimate fate. Could the nature of our thoughts and awareness be explained by the laws of physics? What happens when we die? Not from a philosophical or religious standpoint, but through the lens of science. Even our dreams, those strange, fleeting experiences of the mind, may have explanations rooted in physics and biology. This part will take us through these questions, exploring the intersection of physics and human existence. Section 1. Could consciousness be explained by physics? Consciousness, the experience of being aware, thinking, and perceiving, feels like the most fundamental aspect of existence. Yet despite all our advances in neuroscience and physics, no one fully understands how it arises. Traditionally, consciousness has been studied from a philosophical and biological perspective, but some scientists believe physics may hold the ultimate answer. Could the strange and counterintuitive laws of the universe, such as quantum mechanics, be the key to unlocking the mystery of awareness? One of the most fascinating theories linking physics and consciousness is the idea that quantum mechanics plays a fundamental role in how the mind works. The human brain consists of vast networks of neurons, transmitting electrical and chemical signals to generate thoughts, emotions, and decisions. But some researchers, like physicist Roger Penrose and anesthesiologist Stuart Hameroff, propose that something deeper is happening at the quantum level. Their theory, known as orchestrated objective reduction, suggests that microtubules, tiny structures inside neurons, may process information using quantum mechanics. If true, this would mean that consciousness itself is a quantum phenomenon, entangled with the very fabric of reality. Other theories take a different approach, suggesting that consciousness is an emergent property that arises from the complex interactions of physical systems. Emergent phenomena are those that cannot be understood simply by analyzing their individual parts. For example, a single water molecule isn't wet, but when billions come together, the property of wetness emerges. Similarly, some scientists argue that when billions of neurons interact in highly complex ways, consciousness naturally arises, even if no single neuron possesses it. Then, there's the idea that consciousness is not just a byproduct of physical processes, but a fundamental property of the universe itself. This concept, known as panpsychism, suggests that consciousness exists at every level of reality, from subatomic particles to human minds. In this view, the entire universe may be aware in some basic way, and human consciousness is simply a more advanced and organized form of this universal awareness. Some physicists speculate that consciousness could be linked to the structure of space-time itself, potentially embedded in the very geometry of the universe. Another perspective comes from the field of information theory. According to this view, consciousness may arise from the way information is processed and organized. Some scientists propose that consciousness is not a material thing, but an informational pattern that emerges when a system reaches a certain level of complexity. In this sense, our minds might function similarly to advanced computers, with our thoughts being the result of highly sophisticated data processing. The search for a physics-based explanation of consciousness also raises questions about artificial intelligence. Could a sufficiently advanced AI become conscious? If consciousness emerges purely from complexity, then theoretically, a machine could one day develop self-awareness. However, if quantum mechanics or other fundamental physical laws are essential to consciousness, then AI might always remain something different from human minds. If physics can explain consciousness, it could change our entire understanding of reality. It might offer insights into the nature of free will, identity, and even what happens after death. Some scientists speculate that if consciousness is tied to quantum mechanics, it might not simply disappear after death, but instead become part of the fundamental quantum fabric of the universe. While this remains highly speculative, it shows how deeply the mystery of consciousness connects to the broader mysteries of existence itself. Section 2. What happens when we die, from a physics perspective? Death is an inevitable part of life, yet what happens after we die remains one of humanity's greatest mysteries. While philosophy and religion offer various interpretations, physics provides a different perspective, one grounded in the fundamental laws of nature. When a person dies, their biological functions cease, but what happens to the energy, matter, and even consciousness that once made up their existence? Can physics provide an answer to the question of what happens after death? At the most basic level, physics tells us that energy cannot be created or destroyed. It can only change form. This principle, known as the first law of thermodynamics, suggests that the energy that powered a human being must go somewhere after death. When the body stops functioning, the stored chemical energy within it is released into the environment. This can happen in various ways. As heat, as the decomposition process returns nutrients to the earth, or as energy transferred to other living organisms that consume remains. From a purely physical standpoint, the body does not disappear. It simply transforms, continuing in different forms throughout nature. But what about consciousness? The brain, a highly complex network of neurons, operates through electrical and chemical signals. Some scientists believe that consciousness is simply a byproduct of this neural activity, meaning that when the brain stops functioning, consciousness ceases to exist. From this perspective, death is the end of subjective experience. There is no awareness, just as there was none before birth. However, some researchers and theorists have speculated about the possibility that consciousness could persist beyond physical death. One idea, inspired by quantum mechanics, suggests that consciousness might be linked to the fundamental structure of the universe itself. Some interpretations of quantum theory propose that reality does not exist in a definite state until it is observed. If consciousness plays a role in shaping reality at the quantum level, could it somehow continue beyond the body's death? This question leads to the controversial idea that consciousness might not be entirely confined to the brain. Some physicists, like Roger Penrose, have suggested that consciousness could be a quantum phenomenon, possibly tied to the behavior of microtubules within neurons. If this is true, then the mind might not be entirely dependent on biological processes, opening the door to speculation that some aspect of consciousness could exist independently of the body. Near-death experiences have also fascinated scientists. Some people who have been revived after clinical death report sensations of detachment from the body, seeing bright lights, or even experiencing a sense of peace and oneness with the universe. While these experiences are often interpreted through spiritual or religious frameworks, some researchers suggest that they might have neurological explanations. The dying brain undergoes significant chemical and electrical changes, which could create vivid and unusual perceptions. However, there remains debate over whether these experiences could hint at something beyond material explanations. From a cosmic perspective, our atoms and subatomic particles do not vanish after death. The elements that make up a human body, carbon, oxygen, nitrogen, and more, originated in the cores of ancient stars. In death, these elements return to the Earth, the atmosphere, or even into future generations of living beings. This cycle of matter and energy is a fundamental part of the universe, connecting all living things in a vast, intricate web. Ultimately, physics does not provide a definitive answer to the question of what happens after death. It can explain the transformation of matter and energy, the ceasing of brain activity, and possible quantum or informational implications. But whether consciousness continues in some form remains an open question, one that science has yet to fully unravel. Section 3. The physics of dreaming and the mind. Dreaming is one of the most mysterious aspects of human consciousness. Every night, as we sleep, our brains generate vivid, sometimes bizarre experiences that feel real, yet exist only in the mind. While dreams have been studied from psychological and neurological perspectives, physics can also offer insights into how and why they occur. At its core, dreaming is a product of electrical activity in the brain. During sleep, especially in the rapid eye movement or REM stage, neurons fire in complex patterns, creating dream experiences. Brainwaves, measured in hertz, shift from slow, deep sleep frequencies to faster, more active states during REM sleep. This electrical activity is governed by the same physical laws that control all other processes in the universe, including electromagnetism and thermodynamics. One of the most fascinating ideas in physics related to dreaming is the concept of information processing. The brain is often compared to a quantum system, constantly organizing and restructuring information. Some scientists speculate that the brain might function in ways similar to quantum mechanics, where thoughts and memories exist in overlapping states, collapsing into specific dreams when activated by neural activity. This could explain why dreams feel fluid and unpredictable, much like quantum superposition before observation. Another perspective comes from entropy and thermodynamics. The brain, like any system, follows the laws of energy conservation. Some researchers suggest that dreaming helps to reorganize neural pathways, clearing out unnecessary connections while reinforcing important ones, much like how a computer optimizes data storage. While physics does not yet fully explain dreaming, it highlights the deep connection between the mind and the fundamental forces of nature, reminding us that consciousness itself may be shaped by the same principles that govern the universe. With this, we conclude our exploration of physics and human existence. In this part, We delved into the mysteries of consciousness and whether it can be explained by physics, examined what happens when we die from a scientific perspective, and explored the nature of dreaming and the mind. While many of these questions remain unanswered, they remind us of the deep connection between physics and our own existence.